Problem 7. A sequence with n term a sub n is defined recursively with these initial conditions and this recurrence relation. An is n minus 1 minus n minus 2 divided by 2 for every n greater than or equal to 3. Find the next three terms. To get A3, we substitute 3 for n in the recurrence relation. We get this. Here, A2 is given in the problem to be 46, and A1 is 100. Replace those. Evaluate, you get negative 27. So A3, we determine A3 to be negative 27. To get A4, we replace n with 4 here. We get this. But A3 and A2 are known. A3 is negative 27. A2 is given in the problem, 46. Evaluate, you get negative 73 halves. And finally, you can put this in the calculator and make the calculator compute the fraction. A5, similarly, we replace n with 5 here, we get this. A4 is computed. A3 is computed. Put this in the calculator, it will produce the answer. Problem 8. Solve the recurrence relation. An equals 7an minus 1 minus 10an minus 2 with these initial conditions. A0 is 1, A1 is 8. The recurrence relation is linear, homogeneous with constant coefficients of degree 2. And the recurrence relation and the initial conditions define unique sequence. You can compute A2 easily. Replace n with 2. Then replace A1 with 8 here, A0 with 1. Evaluate, you'll get that A2 is 46. A theorem gives a formula for any sequence that satisfies the any sequence that satisfies the recurrence relation only. To use the theorem, we need to write the characteristic equation. Replace n with 2. You get A2 equals 7A1 minus 10 A0. And then replace A2 with R squared, A1 with R, A0 with 1. Move everything to the left. You get this equation. This is called characteristic equation for this recurrence relation. Find the roots of this quadratic equation. Factoring is easy here, but you can always use a quadratic formula if you cannot see how to factor. Zero product property means R minus 2 is 0, which gives R equals 2, or R minus 5 is 0, so R is 5. Because the characteristic equation has two different zeros, 2 and 5, the theorem says any sequence that satisfies this recurrence relation has n term given in this form. Some coefficient C1 times 2 to the n plus another coefficient C2 times 5 to the n. And we determine this unknown coefficient C1 and C2 from the initial conditions given in the problem. Replace n with 0 here, we'll get A1 equals C1 plus C2. 2 to the 0 is 1 and 5 to the 0 is 1. So this is the first equation. And then replace n with 1, you get this. Because A1 is given in the problem to be 8, you get this equation. Now simplify, you get this system. So C1 and C2 must be solutions for this system. And to solve the system, we multiply the first equation by -2 and add the result to the second equation. This way C1 disappears. 2C2, negative 2C2 plus 5C2 is 3C2, negative 2 plus 8 is 6. Divide both sides by 3, you get C2 equals 2. C2 is 2, so C1 must be -1. And then replace in the formula, in this formula, C1 and C2 is the numbers that we found, and you get the answer. The answer is C1 is -1, so -2 to the n plus 2 times 5 to the n. You should check. Replace n with 2. Evaluate this. -2 squared plus 2 times 5 squared. The result is 46, as before. Problem 9. A club consists of 15 men and 12 women. In how many ways can the club select a committee of 5 persons that has at least 1 man and 1 woman? The committee doesn't have positions, so this is an unordered selection. Each selection is unordered. So you have combinations, regular combinations. So first we count the committees composed with 1 man and 4 women. We can select such a committee in 2 steps. First step, select 1 man. 15 are available. 15 choose 1 selections. These are the number of outcomes of step 1. Second step, select 4 women. 12 are available, so 12 choose 4 selections. The product rule says the number of committees that have 1 man and 4 women is the product of 15 choose 1 and 12 choose 4. Similarly, we count the committees that have 2 men and 3 women. Again, 2 steps. 15 choose 2 outcomes in the first step, and 12 choose 3 outcomes in the second step. So this is the product is the number of committees of this kind. And then we count committees composed of 3 men and 2 women. Again, 2 steps. 15 choose 3 is the number of outcomes of step 1. And 12 choose 2 is the number of outcomes in step 2. And finally, count the committees composed with 4 men and 1 woman. 15 choose 4 times 12 choose 1. Similar 2 steps are used. Because all those committees that have 1 man and 4 women are different from the remaining committees, which have 2 men and 3 women, or 3 men and 2 women, and so on. That is, we have to add those numbers. And this is the answer. The sum of these products. Evaluate this using the calculator. And the output is 76,935. Problem 10. 12 horses are entered in a horse race with first, second, and third prize. In how many different ways can the prizes be given? These selections are ordered selections. Of course, it matters which one is first, which horse is second and third. So these are permutations, regular permutations. And the answer is given by P12(3). We have a formula for this. 12 times 11 times 10, 3 consecutive decreasing numbers are multiplied to get the answer. Problem 11. List the ordered pairs in the equivalence relation on the set 1, 2, 3, 4, which has equivalence classes 1, 2, and 3, 4. To write the pairs in the equivalence relation, we start with writing all possible pairs that have entries from the first subset on. These are 1, 1, 2, 2, 1, 2, and 2, 1. So we are done with the first subset. And then handle the second subset similarly. Write down all possible pairs that can be written using the numbers from the numbers 3 and 4. 3, 3, 4, 4, 3, 4, and 4, 3. And this is the answer. We are done. Problem 12. It is known that a piggy bank contains 20 coins, which can be pennies, nickels, dimes, and quarters. What is the number of possible distributions of coins in the piggy bank? Clearly, the order doesn't matter, the order of the coins. And because you can have many pennies, many nickels, many dimes, so these are generalized combinations. So we count generalized combinations. The variety is 1, 2, 3, 4 kinds of coins, so 4. And we have 20 coins, repetitions allowed. So 4 multi-choose 20. Multi-choose means we have this double parenthesis. The theorem says replace the upper number by the sum. 4 plus 20 minus 1. The lower number stays. This is a regular binomial coefficient. Evaluate, you get the answer.